and lossless is not possible. That's the negative result. Sometimes it is possible, sometimes it is not possible. So that's kind of the key message I want to get across. Okay, the key message I want to get across. So when it is possible, like in this case, it is possible, right? You can decompose this into a set of smaller BCNF schemas such that the decomposition is both GPD and lossless strong decomposition. When it is possible, how do we do it? That's the next slide I'm going to show you. But keep in mind, this is not always possible. This is not always possible. And that's the main reason why people need to introduce other normal forms than BCNF. If it's always possible to decompose the input relation into BCNF and the decomposition is dependency preserving and lossless drawn, you don't need any other normal form because, as we said, BCNF allows no redundancy. That's kind of quote unquote the best normal form you can expect. There's no redundancy. You should always go with BCNF. Unfortunately, this is not always possible. Henceforth, people introduce other types of normal forms. Yeah, that's how all this change together, right? But before we show that, let's look at if such a decomposition is possible, how do you do it? When this is possible, how do you do this? How do you do this decomposition? So the idea is really recursively apply the lemma we talked about, the useful lemma we have. So the idea is you have R, you have F. This is your input. Step one, you check if R in B, C, and F. You always check this first. Step two, if yes, stop. Nothing more to do, right? I mean, if it's already in B, C, and F, don't do nothing. It's already good. There's no redundancy, you can just stop. If not, continue to step 3. And step 3 is, basically, I'm going to write down this lemma, this useful lemma we have to talk about. The useful lemma says if W determines D and you can decompose R into this decomposition is lossless. Right? All you do in step 3 is to recursively apply this result, to decompose R into smaller schema. That's it. Specifically, how do I recursively apply this? Well, you take F and make any functional dependency in F has only a single attribute on its right-hand side. What do I mean by that? Take any functional dependency from F and make right-hand side a single attribute. For example, if you have A determine BC from F, you convert this into A determine B and A determine C. This is always possible, right? Because we have one of the inference rule. One of the inference rule is the decomposition rule, right? If X determines Y, Z, you can always decompose this into X determines Y and X determines Z. We prove this, right? By the way, we prove this using the basic rules. So far, so good. Why you want to do this? The reason you want to do this is to guarantee this condition. The left-hand the left-hand side and right-hand side intersection equal to empty. Why? Because once you decompose into this form, right-hand side is a single attribute, you will get rid of any trivial function dependency, which is not the case in this example. Let's consider another example. Let's say we have AB determine BC from F. AB determine BC from F. You follow this? Now, if I decompose it into a single attribute on the right-hand side, what do I get? I get this. You follow this? And what's critical about this step, by the way? Once you do the decomposition like this, you can get rid of trivial function dependency like such. AB determine B, that's a trivial function dependency. A trivial function dependency means that the right-hand side is a subset of the left-hand side. You follow this? And the significance of this is after this step, for any functional dependency from F, its left-hand side intersect right-hand side, guaranteed to be an empty set because of this. Right? Because you decompose the right-hand side into a single attribute and you get rid of trivial functional dependencies, which means the right-hand side must not be a subset of left-hand side, which means the intersection of right-hand side and left-hand side must be empty set. That's the critical observation we make from this particular step. And once you have this, you can just recursively apply this result. Right? Take any function dependency from F, apply this, you always guarantee to have a lossless strong decomposition. That's it. You follow what I'm doing here? So step 3 is this, step 4, you just recursively apply this for any functional dependency that, of course, you don't have to do this for functional dependency that satisfy the BC and F requirement. If a functional dependency satisfies the BC and F requirement, there's no action to be done. You only need to do this for functional dependency that left-hand side is not a key or super key. Then those are the functional dependency that has violated the BC and F requirement. And you recursively apply this, decompose it, you always guarantee to have lossless strong decomposition. That's it. Okay, so that's this algorithm. What this algorithm doesn't guarantee, however, is that it guarantees to give you lossless strong decomposition, but it doesn't give you dependency preserving. It doesn't give you dependency preserving always. Maybe it will give you, but in some cases it may not. What's the other side product I didn't mention is, if you follow this, the resulting schema is always in BC and F. The resulting schema, set of schemas are always in BC and F. So you get a lossless strong decomposition into BC and F. That's not necessarily dependency preserving. Sometimes they are, sometimes they are not. If you are, fantastic. If you are not, too bad. In that case, a lossless strong decomposition with dependency preserving simply does not exist, or you cannot find it in polynomial time. Okay, so that's this idea. Let's look at a concrete example of this algorithm. Then we're done, right? Then we're done. So suppose I have this this schema. This is the same schema as we talked about before. You have contract ID, supply ID, product ID, department ID, part ID, quantity, and value, which tells you under this contract, this department will order this part from this supplier for this much quantity, for this much value. Okay? That's the schema we talked about before. And I have this set of functional dependencies to start with. You follow this? Okay, we actually seen this example before, right? So let me apply this algorithm to this schema. So my CS and my functional dependency is C determining everything. So what this function division means, we talked about this before, right? Take this as an example. Take this as an example. What does this mean? Can someone tell me what JP determinacy means? We talked about this before. In plain English language, what JP determinacy means?
It's a key.
JP is a key, yes, but translate that to English. What does this function capture? What kind of constraint it capture from your user specification? What's the language in user specification that will translate to this JP determinacy? For the same product and for the same part, you always order that part for that product under only one contract. Right? That's what we said last time, right? Product under just one contract. Meaning that you don't order the same part under multiple contracts for the same product. We talked about this before, right? Remember? Okay, what's going on here is like you have Star Wars movie has a series, right? So instead of asking you what happened in the beginning of today's movie, I ask you what happened in Star Wars #1. You're watching Star Wars sequel #2. If you really claim you're a fan of Star Wars, then you should be able to answer this, right? We went over this. You watched this movie before, trust me. Okay? All right? You know, sometimes it puzzles me, right? Why, you know, a person can remember everything from Star Wars without any problem. A sequel of 6 or 7 movies, and after 2 lectures, you know, you forget what happened in last lecture. And to me, it's just like watching mini Star Wars in multiple lectures. You know why? Can someone tell me why that's the case? That's because you're interested in the content. That's because you're interested in the content. Humans are really good at understanding and memorizing stuff if he or she becomes interested in the content. And you don't need to offer any more incentive than that. Sometimes you do, right? Sometimes a person may not be interested in the content, then you offer some incentive, like if you remember this, I offer $1 million. I'm sure you will remember it. But sometimes, if it's a Star Wars movie, I don't offer you any monetary incentive, you will still remember the content because you just got interested. And the fact that you forgot about this means that you're not interested in this stuff. Which is fine, I'm going to offer you an incentive. That incentive, unfortunately, is not monetary. The incentive is, if you remember this, you will do well in the exam. And too bad, that's just a sufficient condition, and it is also a necessary condition, meaning that if you don't remember it, you won't be able to do well in the exam. So I will make both that a sufficient and necessary condition, meaning that you have to remember this, okay? Whether you are interested or not. Go ahead.
So, with regard to your question about this, what I remember is, did you say that you said to answer what it means in English?
You mean how do you translate from here to here?
You said to answer what this means in English. I remember you talking about you bought it when you buy these parts for the same under one contract, you get a better price. That's all I remember.
I don't know what you're saying, but let's go back. Let me spend some time to revisit this, right? So you have J, P, and C. You have some other attributes. So what this said, if you have JP determined C, let's say your product number is product 1, part A, and you have a contract, let's say contract 01. Meaning that you are buying this part A for product 1 under contract A. If you have JP determined C, what that means? Sometime later, you see another product 1, meaning that product 1, and there's a quantity, right? Quantity and value. Let's say you buy 10 and you for $100. And later you say, I'm going to buy this, too bad, I need this part again. I'm going to buy another 20 of this. This time, price, too bad, price increase. Instead of $200, this becomes $500. You follow this? The argument is, okay, I'm going to do this under another contract. The question is, can you do this with JP determine C? Can you do this? If JP determines C, this is not possible. This is the X, this is the Y. When projection of X are the same, projection of Y must be the same. So it has to be under the same contract. The point of what I said last time is to prevent things like this happening. You want to buy something, you buy in big quantity. You make sure you get a good deal out of it. Instead of buying in multiple smaller quantity under a different contract. You got a bargain of wholesale. That's the point. That's what I said last time. I said this again this time. Don't force me to repeat this before the final test. Right? This is common sense. You look at this, what's going on. So functional dependence looks complicated, looks contrived, but it's really just common sense. It's really important. This stuff is really important. I mean, not only is it important for database, later on when you guys are ready to buy a house, maybe you bought a house already. Too bad, you didn't know functional dependency back then. Go back, revisit your contract. Okay. Later on in your life, if you buy a house or enter an agreement with someone, apply this stuff we said today. Check those contracts, make sure you don't get into some sort of trouble, right? Okay, so that's this. But that's not really the point I'm trying to show today. What I'm trying to show today is to check, is this, so step one, right? Like I said, is this in BCNF? Can someone tell me, is this in BCNF? Is this in BCNF? Is this schema in BCNF? Well, let's check. Right? First of all, this one is okay. Right? Why? Because the left-hand side is the key. What about JP determine C? Well, JP determine C, C determine everything else means that this is the key. So this is okay. This satisfies BCNF requirement. What about this? SD determine P. Boils down to is SD a super key? To answer that, we are simply checking the closure of SD, which start with SD and P. Anything else you can derive from this? Nothing. Nothing you can derive from this, so no. Which means this has Bartlett BCNF requirement, so this is not in BCNF form. In other words, SD determine P introduce redundancy to your schema. If you stick with this design, you're going to end up with insertion, deletion, update anomaly. All these bad things we talk about. You follow this? Okay. At this point, you already know R is not in BCNF, but let's just check, right, for the sake of curiosity, right? What about this? Is J determining S? Does J determine S wireless BCNF requirement? Well, you check, right? I mean, essentially it boils down to is J super key. In this case, because J is a single attribute, this is essentially saying is J a key, right? Because if J is a super key and a single attribute, it must be a key. To check that, you check the closure of this. It's just J and S. Nothing else, then you can stop. You claim this is not a super key, hence it's not a key, so no. So both of this has valid BCNF requirement, which means this design is not okay. If you go, of course you may argue, what do you mean it's not okay? Yes, I understand I have insertion, deletion, update anomaly, but in my application level code, in my Java code, PHP code, C++ code, I will make sure those anomalies are taken care of. You follow me? Yes, in that case, yes, of course it's okay. But the key observation is, if you go with that, you complicate the task of the developers on top of your database, who work on top of your database. It's kind of like, imagine you are sending your troop to fight a war, right? You give them a bunch of just guns. Can they win the battle? Yes, they can, right? I mean, but with greater effort. Does that make sense? You don't give them the tank. You don't give them, anything else. Just give them a bunch of guns. Of course, with bullets too. Right? So can they win the battle? Yes, but you're making them to pay extra effort. It's kind of like you're making your developer to pay extra effort for a faulty design that you come up with. That's kind of what's going on here, right? So when I say, is this okay, it's always a relative sense, right? Of course, you can live with anomaly like that. Insertion, deletion, update anomaly. You're pushing off that responsibility to the application developers in that case. Do you follow me? Right? Okay. So let's say you don't want to push this off to the application developers. You want to take care of this for them so that they can write simpler code. Meaning that when they write their code, they don't have to worry about any of these anomalies. For example, when they update the value of P, they don't have to write that update statement in an atomic unit such that when they update 1,000 records, those 1,000 updates must happen together. Because otherwise you end up with update anomaly. Some P end up with a different value than some other P when SD value are the same. So you can of course do that in an atomic unit in your code. Does that make sense? Like using something like semaphore, which we will be talking about very soon, right? When we talk about transactions. But it's better that it's much nicer for a developer to say, I don't have to worry about these low-level details. I can just write update P independent of the update of other P values in my code. I don't have to worry about this kind of things. Do you follow this? Okay. All right, so let's take care of this. So step 1 is done, right? No. Step 2, make right-hand side single attribute. This is easy, right? In our case, everything is on the right-hand side is already a single attribute except C determine everything. So you break C determines everything into C determine C, C determine S, C determine J, so on and so forth until C determine D. And after this, you get rid of this trivial function. You get rid of that. Of course, we keep the other ones too. Right? The other ones are already in the form of having right-hand side as a single attribute. Okay. Next, you apply this rule of W determines Z recursively, but you only do so for those functional dependencies that have violated the BCNF requirement. For those who satisfy the BCNF requirement, you don't have to worry about it. They're fine. You don't have to do nothing about it. For example, take C determine S as an example. This is okay because C is a key. So the left-hand side is the key, so this satisfies the BCNF requirements. All of this. And here's for this satisfies BCNF requirement as well because JP is the key. This one, however, violates the BCNF requirement, right? You follow this? And you take this as your W, this as your Z. You decompose R into R minus V and WZ, which gives you what? This is your R, right? And this is your Z. SD is your W. You follow this? R minus Z give you C, S, J, D, Q, V. WZ is SDP. You get this. And this decomposition is guaranteed to be lossless. Why? Because we are applying this useful lemma. If you don't believe me, you can check. What's the intersection of the two? The intersection is SD. And SD determines SDP, meaning that if you take this x, this is the y, x intercept y equals to SD, determines y equals to SDP. So this is guaranteed to be lossless. It's guaranteed to be lossless. Do you follow what I'm doing here? The question is, but lossless is just one side of the story, right? You want to ensure two more things. One is the resulting decomposition is dependency preserving, and they are in B, C, and F. Otherwise, you're not done yet. If they're not in B, C, and F, you should keep decomposing them. So let's check. Is Y, B, C, and F? Is F is X, B, C, and F? Let's start with the simpler one. Is Y a B, C, and F schema? Can someone tell me? In order to check that, you need to find the projection of the dependency Fy onto Y. What's Fy in this case?
Sorry, quick question. What's X and what's in Y? What's in Y? Oh, sorry.
Okay. What's the projection of Y? Fy in this case? What's the projection of function? We talked about this, right? How do you check the projection of this? You take the closure of this. By the way, the closure in this case is simply Excel, right? It's adding JP determines everything. Right? That's the only additional function that you can derive. The rest stays the same. You take that and you project onto SDP. What do you get?
SD determines P.
The only thing you get is SD determine P. That's the only dependency involving only attribute from Y. What's Fx? You still have C determines everything.
And also,
Right? You also have, do you have SD determine P? No. You don't have P here anymore, right? You only have SD. What about J determine S? Yes. That survives because both J and S are here. What about JP determine everything? Obviously that's gone because P is no longer an attribute here. So you end up with this. That's it. That's Fx, that's Fy. Yes?
Why did we keep C determines everything?
Oh, by the way, this everything is not the same as everything here. This everything prime is like everything here.
Oh, okay.
Okay. Very good observation, right? When you talk about mathematics logic, you have to be precise. When you say everything, what do you mean by everything? Right? Everything with regard to X, okay? Not the original everything. Because P and S, P is no longer there, right? Okay, is Fy in B, C, and F? Is Y in B, C, and F with respect to this? The answer is yes, right? Because you have three attributes SDP. The only function dependency you have is SD determine P. SD now is a key for Y, right? Obviously. So this is okay. What about this? What about X? C determine everything prime means that C is still a key, so this satisfies B, C, and F requirement. What about J determine S? What about J determine S? The answer is no, right? It's not in B, C, and F. It is not in B, C, and F. Because J is not a key. J only determines S. The closure of J is just JS. That's it. So this part is B, C, and F. What do? You recursively apply the same result. You take this as you R, you take this as you F, you do exactly what we did. In other words, continue here. You take, I'm going to copy this. You decompose this into x1, y1. Y1 is, this is your W, this is your Z, it's JS, WZ. And this is simply R minus Z, meaning that you minus S. You got C, J, D, Q, B. Now you're done, right? Because the projection of this is J determine S, meaning that this is now in B, C, and F. This, the projection onto this is C determine everything else. This is okay. So your final decomposition, using what we said is this, and this. This is gone. This is decomposed into two smaller relations. That's how this algorithm works. You just recursively apply the same algorithm until everything is in B, C, and F. That's it. It looks a little bit complicated, but actually concept-wise it's really straightforward. You're doing the same thing over and over again until everything is in BCNF. And you don't have to worry about losing any information, because if you follow strictly what we said, every step is guaranteed to be lossless translation. You follow what we're doing? So essentially, it's kind of like you're building a tree-like structure while decomposing this. Every leaf level node is a BCNF schema. If you have a node that's not in BCNF, you further decompose that into two smaller. Question?
Just making sure, when you are saying in step 3 about Fy and Fx being, well, Fx not being BCNF, but Fy being BCNF, it's for this.
X is not BCNF
yeah.
because Fx has J determining X, and J is not a key.
And we're appropriating it to the attributes we have for X per Y.
Of course. Okay, so to summarize, you start with R. The whole process is like this, right? You start with R. It's like a tree. You start with R and F. You decompose R into R1 and R2 using 1 FD from F that varies BC and F. Then you check. If R1, you got F R1, you do the projection onto these two, and you further decompose this if R2 is not BC and F. And you decompose this into R21 and R22, again, using one functional dependency from now FR2 though, from the functional dependency from that varies BC and F. And you continue with this process. That's essentially what we're doing. Every step, if you think about it, every step like this is identical. You're doing exactly the same thing recursively. Using this lemma, decompose into, right? So that's essentially what we're doing. Looks complicated, but really not. Really, that's all we're doing. That's all we're doing. Okay. The question though is, at the end of the day, you end up with this, this, and this. You stop when all the leaf level nodes leaves are BCNF, right? Leaves are BCNF. This guaranteed to be lossless, but does this guarantee to be dependency preserving? Let's check in this case. Unfortunately, in this case, we end up with this. We end up with this and this, right? This dependency of JP determines C, you can check using this, this, and this. It's lost. So dependency preserving is not satisfied. You follow this? Yeah? So how do we fix this problem? Unfortunately, okay, let me use 1 minute to talk about it, because if I don't mention this, it will be 2 weeks down the road, right? Because there's the midterm, then there's the spring break. I guarantee you when you come back, you will forget it. It's not a Star Wars movie, right? So you will for sure forget it. Okay. So the way to fix this, do you see the problem? So I know it's lossless strong decomposition, but we don't have dependency preserving, right? We don't have DPD. How do we fix this? A hack. It's kind of like when your fridge stops working, what's the first thing you do? When your fridge stops working, what's the first thing you do? You don't call somebody, right? Because you are not paying money if you do that. You shake it. You kick it, you shake it, and sometimes they bring it back. Seriously, that's what I do. So it's a hack. The hack is really simple. Is okay, this is lost, right? I add GPC as part of my decomposition. I add a schema that's just union the right hand side and the left hand side of that loss functional dependency, JPC. I add that to my decomposition. So my decomposition is this, and this additional one to preserve the lost dependency. I do that. That's like a hack, like kick your fridge. Kick really hard if it doesn't work, right? So, is this a good solution? Is this a good solution? It depends. In this case, it's not too bad. You end up adding just one schema back. But in some more complicated cases, remember I show you, when we talk about ER, I show you a ER from the Department of Land Design, Landscape of something. The ER is like 2 pages, right? In cases like those, meaning that you have really complex schema, you may end up adding a lot of such hacks. You may add up too many patches. And eventually it will break. Hence, for people look for a better solution, which is to introduce a more relaxed normal form, which is a third normal form. That I can talk about after the break. It's like Star Wars sequel number 3. By the way, I will release homework for today.